everyone, welcome to Making Predictions with ArcGIS. I'm Mallory Delgadillo, Esri Product Marketing Manager for our Data and Analytics products, and I'll be your moderator today. Today I'm joined by my Esri colleagues, so I'll go ahead and let introduce themselves. Omar?
Hi everyone, my name is Omar. I'm the Global Director of AI and Machine Learning in the Global Business Development.
Hi, I'm Flora Vale. I'm a product engineer on the analysis and geoprocessing development team.
Hello, I'm Oren Aiden. I'm a senior researcher in the spatial statistics team.
Thanks, guys. So with that, I'll go ahead and turn things over to you, Omar.
Thanks, Mallory. I want to start by thanking everyone for attending today. This is a webinar among our GeoAI webinar series. We've been delivering different webinars about object detection and feature extraction from imagery, analytics and natural language processing. We've been delivering some specific industry-related webinars like national mapping and statistics and AI applications in transportation. And all of these webinars, you're going to find it in the events page under spatial analysis and data science. We're going to share a link for that. And making predictions is one of the most important aspects of spatial data science or GeoAI. Predictions that are geospatial in nature, like predicting road crash risk or predicting best areas to open stores or predicting disease propagation, for example. For these kind of predictions that are geospatial by design, we're going to see today why ArcGIS is really essential and why GIS in general is really essential, whether in modeling the problem or really preparing the data. I want to start by sharing our outline today. We're going to start with a quick intro about AI and data science in ArcGIS, and then defining what is spatial data science really. We're going to talk about models and have a quick dive into generalized linear regression and geographically weighted regression. We're going to discuss forest-based classification and regression, which is a tool that we have in ArcGIS that can help with making predictions. We're going to understand the concept of training and how to evaluate model performance. And then we're going to start showing different demos. We're going to start by 3 different demos for these tools. We're going to see in action these tools in Pro, and then we're going to follow up with a demo integrating with external machine learning framework, right? So we have tools in Pro that we're going to see, and then we have an integration capability with whatever machine learning framework that you're using. We're going to see how we are doing this kind of integration through ArcGIS notebooks and Python API and ArcPy. And then we're going to close with useful resources and open Q&A. So if you have any questions, feel free to share them in the chat box, as Mallory mentioned, and we're going to answer these questions towards the end. So machine learning, deep learning, AI, scikit-learn, we keep seeing and hearing these buzzwords every now and then, right? And the fact that this field in general is growing a lot, but it really boils down to 3 main categories, right? So that's the way at least we personally see it. So you can think about it that AI is the big idea of achieving human-level intelligence, and this idea has been around since the 50s almost, right? It's not a new idea. Machine learning is a field of AI that's about learning from data to derive rules and extract patterns instead of being explicitly programmed. And deep learning is one kind of machine learning. It's using specifically deep neural networks, and it's recently becoming very good with high-dimensional data like voice, images, and text. ArcGIS is a scientific platform that provides these capabilities, in fact, to serve the purpose of spatial analysis. And if we want to have a quick bird's eye view on the capabilities in ArcGIS that supports AI and data science, you can think of these main building blocks, if you will. So we have data engineering capabilities that can help you prepare the data, process the data, clean the data, right? So this is a very important step before doing any modeling, really. We obviously have a lot of visualization and exploration. You can use the different visualization, the beautiful maps, the different kind of symbology to visualize the results and show the patterns, whether you are still in the exploratory data analysis phase or after you're done with your work and you want to communicate your results. At the heart of our tools is obviously the spatial analysis tools, right? That's the whole essence of this kind of direction, that you want to solve a spatial problem at the end of the day, right? And hence, complementing your analysis with spatial analytics is very important. We have machine learning and AI capabilities, right? So we can think of predictive analytics. We have a lot of tools that can help make predictions that we're gonna see today. We have a lot of tools that can help you understand patterns and do clustering for the data. We have deep learning tools that can help you detect objects and extract features out of imagery, different kinds of imagery and LiDAR, oriented imagery, videos, you name it. We have capabilities that can help you put these models into production, right? If you have massive data, we can deal with this, whether it's raster or vector. So we have geoanalytics that can help you deal with large amounts of data, do the processing, and even do machine learning with large amounts of data. If you have large raster data, we can leverage distributed raster analytics with image server to do that. We have modeling and scripting capabilities. So if you want to automate your workflows using Python, for example, you can use ArcGIS notebooks for that. You can use ArcPy, you can use the Python API for this as well. And finally, we have a lot of sharing and collaboration capabilities. You can share your work, share your analysis by different means. You can upload your notebooks, for example, as items on Portal. You can share your models as items on Portal. You can share your code in different ways. So I really invite you to have a look at these different capabilities at the spatial analysis and data science landing page. We're going to be sharing this towards the end. But I want you to think about the analysis as a continuum. It's not just machine learning or AI, it's a continuum of capabilities that you leverage in different phases along the analysis process. And honestly, there is no specific piece that is more important than the others. All of them are really important based on the nature of the problem you're trying to solve. So with that said, I want to pass it over to Flora to walk us through what is spatial data science. Thanks.
All right. Thanks, Omar. Can everyone hear me and see my screen okay? All right. Thank you. So what is spatial data science? I think that data science is a term that we hear a lot, and it can kind of be almost a little bit of a buzzword, but when it comes down to it, spatial data science and data science in general is about solving problems. It's about using data and turning it into information using different methods and algorithms. And really, spatial data science is unique from just traditional data science because it actually incorporates spatial characteristics such as coincidence, connectivity, area, orientation, length, direction, proximity. Proximity is a really big one. The first law of geography states that things that are near each other are more related than things that are farther apart. And so this concept of proximity, or what it means to be a neighbor, is really important in spatial stats and spatial data science in general. So I want to focus this morning on creating models and making predictions. And so we're going to talk about some of the methods that we have available in ArcGIS to generate models and use them to predict unknown values. Okay, well, let's start from the beginning. What are models? Well, models are representative generalizations that are used for prediction. So you think of like a model airplane. It's like a little mini version of the real airplane, but it's generalized. You can think of a model citizen or maybe even a fashion model, although I don't think that those are very generally representative of the population, but you get the idea. A model as a concept, it's a generalization that we use to make predictions. And so why do we model? Well, we want to use information that we have to predict information that we don't have. So we could ask questions like, which buildings might fail inspection? Or what drives sales? Even, what will the weather be tomorrow? That's a classic prediction problem. So we have, we can kind of think of prediction in these two buckets. We have classification and regression. Classification is when you want to predict a categorical variable. So presence or absence of something is a category, yes or no, pass, fail. Crime type is an example, species distribution. Dog breed is kind of a silly one that I'll use as an example a little bit later. And then regression is when we want to predict a continuous numeric variable. So that's going to be something like healthcare spending, mortality rate, sales profits. But when modeling, and this is really true of any modeling method or algorithm that I could think of, you really can't just blindly throw your values in and then trust the value, the first thing that comes out. There's a lot of work we need to do to make sure that we can trust our model, to make sure that our model can actually generalize beyond the data that we use to train it with and predict in unseen data, because that's the whole point, right? We don't need to predict things that we already know. So we need to make sure that our model doesn't just mimic the noise, doesn't just model the noise in our data, but it actually generalizes a trend. And of course, we have to be careful with relationships as well. So I think we've all heard the phrase that causation or correlation does not imply causation, which is true. And here are a couple of funny examples that I like to show. So the divorce rate in Maine is very strongly correlated to per capita consumption of margarine. Now, I myself have never been married, but I don't think that margarine is causing divorce. Or maybe it is, because butter is obviously better. Or another example, the number of people who drowned by falling into a swimming pool versus the number of people, or the number of Nicolas Cage films, excuse me. So I myself, again, not a huge Nicolas Cage fan, but I will not be drowning myself in a swimming pool because of his films being released. So again, these silly examples to show that just because things are related does not mean that one causes the other, and it does not mean that changing one will change the other. So there are many, 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 many ways to model. We have several in ArcGIS. I'm going to describe a couple here that we have available in the Spatial Statistics Toolbox. So we have two linear methods that we're going to talk about, ordinary least squares, or as we are now calling it, generalized linear regression, because we actually include 3 different model types in there, and its spatial counterpart, which is geographically weighted regression. And then we have a machine learning method, forest-based classification and regression tool, which uses the random forest algorithm under the hood. So let's take a quick look at how these methods work. Generalized linear regression models linear relationships. So really, it's a statistical process for estimating linear relationships between variables. So I say linear, but we have 3 model types. And essentially, these are all linear, but there are some transformations that kind of make them fit that linear trend. So Gaussian, the continuous model, that's what we're most familiar with. And that's kind of when you have this continuous numeric variable. Examples of this could include sales, profits, mortality rate, temperature, spending. We also can use a logistic model type with generalized linear regression. And that's when you want to model a binary variable. Yes, no, presence, absence, pass, fail. And then the third is the Poisson distribution, which is when you want to model a count variable. So how many traffic accidents, how many sales will we have in a month? This can also work for rates that are a number over another. So number of people with cancer per 10,000. This could be the appropriate model type for that type of question. And to see how generalized linear regression works, let's take a quick look at ordinary least squares, which is the most simple and basic form. And so we have this equation. And really, this is kind of just the map for how we use explanatory variables to try to predict a dependent variable. So the dependent variable is the y. It's the variable that we're trying to understand or predict. The x's in the equation are the explanatory variables. So that's the information that we do have, that we're going to try to use to predict the information that we don't have, which is that y. And along with the variables that we're going to use to explain the dependent variable, we also have coefficients. And so those coefficients are going to determine the strength and type of the relationship that the explanatory variable has to the dependent. So you could have a positive relationship, a negative relationship, or you could have no relationship at all. And then the last thing in this equation that's actually really important is the residual. So these are the model over and under predictions. Essentially, this is the error term. So when you fit your data to this line, we have our predicted values right along that line, and the observed values kind of fall around the line because no model is perfect. So you're never going to have a one-to-one prediction. And if you do, then you probably did something wrong. But so since we're always going to have those over and under predictions, it's important to understand how far off we are from that line, because that's going to be one of the ways in which we evaluate our model performance. And evaluating model performance, like I said, is really important. In order to be able to use this model for prediction, we need to look through the model diagnostics and try several different models, compare their outputs, compare their diagnostics, and see which one does best. And Oren's going to talk a lot more about these diagnostics in a bit. So I'll just move on to geographically weighted regression. So this is also a linear method, but it's a spatial method. So it's kind of, I think of it as the spatial counterpart to generalized linear regression. And what happens with GWR is that each feature in the data set is going to get a separate equation. So each feature is going to have a neighborhood calibrated for it, and that neighborhood is going to be used to find that regression equation. And once that is found, that equation will be assigned back to the parent feature. And each feature is going to get an equation. And what's really neat about that is that not only does it allow the relationships to vary spatially, which is really important because, as we all know, geography really matters, location matters, and things vary spatially. But it also gives us some really neat opportunities for visualization. So we can actually map something like the local R-squared and see where the model performs best in our study area. Or something like coefficients can be really interesting. Remember, those are the kind of beta symbols, the B symbols in the equation, which determine the strength and type of relationship. So you can tell by symbolizing the coefficients where you might have the most opportunity to influence your dependent variable by changing that explanatory variable. Okay, so moving on to forest-based classification and regression. So now we're going to be using machine learning for prediction. And I'm going to explain how this works with a little example for predicting dog breed. So every model requires training. It's a really important thing in machine learning. The machines learn by training. So I'm going to train my model how to predict dog breed by giving it some examples of dogs and their breed with some explanatory variables. So for each dog, I have the variable to predict, which is the breed, and then I have a set of explanatory variables: size, color, fur, ears, tail, age, and weight. And I want to see if there's any way to combine all those explanatory variables in whichever way possible to have the answer output dog breed. And so the way that this works for a random forest algorithm is by making decision trees. So decision trees are kind of like flowcharts. They create a set of rules for predicting a feature's category or value based on its attributes. So you can kind of think of it like this. If I were to ask my model to predict this new dog's breed, I gave it all of the explanatory variables, but I don't have the breed. So I'm asking the model to predict that for me. So here's my data set, and it's going to create a decision tree based on those variables. So it's going to say, okay, size. Is it a big dog or a small dog? Well, this one is a small dog, so we're going to follow that branch. And color, it's black and tan, so we'll follow this branch. And then ear type, floppy ears. We're going to follow that branch, and the tree has identified the dog as a dachshund. Now that's a very oversimplified explanation of a decision tree, but really it's the concept that you need to understand more so than the deep mathematics of how the branches are split and those sorts of things, which are very interesting. And I really encourage you to read the documentation that we have and that is available in many, many places, because Random Forest is an open source and very popular machine learning algorithm. So I do encourage you to learn more. But here conceptually, random forests are made up of lots of decision trees. So what makes the random forest algorithm so powerful is that it creates this ensemble of trees, hence the name forest. And the reason that it's called a random forest is because each tree is trained using only a random subset of the training data. So it's not going to get all of the examples, and a random subset of the explanatory variables. So it's not going to get all of the attributes either. And so then each tree in the forest, it's going to do its best to predict given the random subset of data and variables that it got. And so you can see the tree on the left got weight, color, fur, and tail, and it correctly identified the new dog as a dachshund. The tree in the middle, however, it got color, fur, tail, and age, and it incorrectly identified the dog as a German Shepherd. But in the end, the majority vote wins, and the forest correctly predicted the new dog's breed as dachshund. So the reason that we use the forest instead of a tree is that any individual tree on its own is not a strong predictor because it's really prone to overfitting to the training data. Overfitting happens when the model mimics the training data set too closely instead of generalizing a trend. And when that happens, if you take that model and try to apply it to new data, it's not going to be able to predict anything because it didn't generalize. And the noise is not going to be what is important for prediction. And so we really need to make sure that our model is generalizable so that it can predict features or values for features that have not been seen yet. And so, of course, evaluating model performance is going to become really important for this method as well. And there are different diagnostics, but one really important thing that we do here, and that should really be done in most modeling efforts, is to hold back some of your training data for validation. So we give our models a bunch of training data that has all of the explanatory variables and the dependent variable. It has the answer to the question because you're using it to train. But we then need to give the model some questions it doesn't have the answer to yet to see how well it does. And so if we hold back 10% of the data, we hold back 10% by default, but you could hold back more or less. After we've trained the model, then we can take that 10% and run it back through the forest to see how it can predict that unseen data. And that's going to give us some really valuable insight into whether or not our model is overfit or whether or not it can generalize and predict well on unseen data. With random forest, there are other diagnostics as well. One is out of bag errors. So since each tree only gets a random subset of data and variables, the tree after the model is created will run the data that was excluded from each tree back through that tree to see how well it did. So that's another way of evaluating the performance. And then we get some really useful information about variable importance. So really, any model is only going to be as good as its explanatory variables, right? So the variable importance chart tells us how useful each explanatory variable was in generating a prediction. For example, we can see here that age didn't really make much of a difference here. It wasn't very useful for predicting dog breed. So all these diagnostics and more can be found in the messages window when you run the forest-based classification and regression tool. And any other of the spatial stats and spatial data science tools will have some rich results that help you determine whether or not your model is a model that you can use to predict. And so really quickly, before I hand it over to Oren to show us some of this modeling in action, I want to describe the modeling workflow in a kind of oversimplified way. So I started with step 1 when I made this list originally, and that's you train your model, and then you evaluate your model performance like we talked about, and then you train again with different parameters, and you compare those models. So you generate many models with diagnostics and then compare all those diagnostics. You might try the same method, say random forest with different parameters and compare those, but you might also try different methods against each other to see which predicts best. And then you repeat that to infinity. And eventually, hopefully you'll find a model that predicts well and you'll use that model, the best model that you found, to predict unknown values. And a very important note I like to end with here is that essentially all models are wrong, but some are useful. So thank you, and I will pass it back over.
Thank you, Flora. I think everybody can see my screen. Today I'll be talking about different examples of workflows that we can employ in ArcGIS for regression. The first one is going to be on a continuous value prediction. So this is what we call Gaussian regression as well. And this is going to be a price model for King County, Washington. And the second example is going to focus on classification for habitat delineation. And the last one will be count prediction to model death counts in the city of Tokyo. So without any further ado, the first demo is going to focus on creating a house model in King County, Washington. So here is a map of this data set. And for those of you who are interested in Kaggle competitions, this used to be a machine learning competition. And today's story about this demo is kind of going to be an underdog story that actually the algorithm that performs the best might be the one that you may not think is going to perform the best. So without giving too much, I would like to first talk about this data set. So at every location, we have the price of the house, the number of bedrooms and bathrooms it has, the square footage of living, that's basically the square footage of the house, excluding the garage or a basement, the square footage of the entire lot, number of floors, whether it's on the waterfront, whether it has a view. The condition and grade are discrete variables that quantify the current condition of the house. Is this in very good shape, used with new materials? Is this an old house that hasn't been renovated? So these two variables quantify that. So our goal here with regression is if we can relate different attributes of a house, such as the number of bedrooms and bathrooms and so on and so forth, to the price, we have a predictive model that can predict house sale prices. This is very useful to understand market dynamics in the context of exploratory regression. From a prediction perspective, this is also very useful. Say you renovated your house or you built a new house and you don't know how much you should charge for it. A model that captures the complexities of housing market and the house price can actually give you a very good idea about how you should be pricing this particular home. The first step we always do before any analysis step is to explore our data. Well, of course, we clean our data. In this case, I start with data that's already cleaned. But the next thing I would like to do is understand these relationships before I start modeling them. So for that, I'm going to be using one of ArcGIS Pro's charts, which is the scatter plot matrix. This summarizes relationships between different variables. Here, my target variable is price. This is what I would like to predict. And everything else is a potential exploratory variable. The first model I would like to use is the simplest model possible, which is GLR, Generalized Linear Regression, and some of you might know it as OLS as well. So this is basically fitting a line to some of these explanatory variables to predict price. So what do I need here? I need an explanatory variable that is highly correlated, linearly related to the price. And here in these boxes, we summarize R-square, which is the amount of variance that this variable explains for the price. The darker the blue, the dark blues indicate high R-square, meaning that high linear relationship, and values of 0 indicate no relationship. Also, you can click on these little boxes to see an actual scatter plot that shows you the actual data in the scatter and also the model line. Here, to predict price, I see two dark blues, square footage of living and grade, the condition of the house. So at first sight, you might be thinking then, let's just define a GLR model, a linear model, where grade and square footage of living are explanatory variables. Well, we know that there is a problem. There's a shortcoming of linear regression, that is multicollinearity. What is multicollinearity? The multicollinearity problem arises when you have two explanatory variables that are linearly related to each other, because they might be bringing the same information to the linear system, at which point the variance is going to start inflating because you have an uninformative variable in your regression model. So as a rule of thumb, we want variables that are linearly related to the target variable, and we want these variables to be not linearly related to each other so that they are bringing in brand new information about the system we're modeling. So let's quickly check this on this chart. Let's go to the chart item for grade and square footage of living, which is this box over here. And they do have quite a strong relationship that is linear. So if I use both of these variables in my linear regression model, I am going to run into multicollinearity issues. So what should I do? I can just create a very simple model with one explanatory variable that has the highest R-square, which is square footage of living. And basically, this is going to be the model I'll be fitting. So let's go ahead and explore this. This is the generalized linear regression tool that you can use to fit linear models. Here, my feature class is the King County housing data, and I would like to predict price. The model type is continuous when we're predicting a continuous variable, and price is a continuous variable. But there are logistic and Poisson modes to this tool as well, so that you can do logistic regression or Poisson regression to predict binary variables or counts. So we will use Gaussian, and we will use square footage of living as our predictor. When we run this tool, this is the output map we get. And also a message screen that tells us some diagnostics about this model. Let's look at the diagnostics first. Coefficient basically tells us how much of a unit change does a square footage of living correspond to for price. In other words, when we have 1 unit change in square footage of living, the price will go up by $280. So when you add 1 square foot to your living space, you basically add to the price on average $280 in this global model. But before reading too much into the regression diagnostics, let's see if this is a valid model first. The first thing we do is check the Conquer BP statistic. And if it is significant, which it is because it has an almost 0 p-value here, that means that there is non-stationarity. In other words, the GLR model might not be capturing the relationships efficiently because the relationships between the variables we use are really changing throughout the study. So there's a geographic component. And the next statistic we'll look at is R-square. R-square basically gives us an idea about the goodness of fit for this particular model. Here we have 0.49. This is not a very strong R-square. We would like this value to be close to 1. We can also check out the joint wall statistic that tells us the significance of this model. Since we have a low p-value, this is a significant model. What does a significant model mean? Well, this is still much better than a random guess of the price. So it is capturing some relationships, but it is not a very strong model. The last statistic I would like to check before I move on to the map is the ArcGIS statistic. This gives us an idea about biasness. What is biasness? Ideally, we would like a regression model to underpredict and overpredict the same amount. But if a model is always underpredicting or overpredicting, it's biased towards an underprediction or an overprediction. And here, a significant ArcGIS statistic tells us that our model is under or overpredicting the price consistently. So let's see if we can see this on the map. So here, you might be thinking, this is a symbology of the predicted values, but it actually is a symbology of standard deviation. Basically, the mismatch between what we predict and what the actual value is. Remember, I am just trying to create a model that'll explain my data. I'm not trying to forecast or predict new data yet. The dark colors indicate significant over and under predictions. And this is the beauty of doing this analysis, even for a non-spatial method in GIS. When we map standard deviations, you can see a spatial pattern. We are actually underestimating house prices around Lake Washington and Lake Sammamish, meaning that we are not taking into account an important factor in this problem, which is distance to water bodies. And remember, our Huckleberry statistic told us that our model is biased. So let's take a look at some of the charts that the tool creates, such as the distribution of standardized values. When we look at this chart, we see that the mismatch between our model and the real data has some skewness to it, meaning that it's not centered around zero, it's skewed away from the mean, which means that this model is actually consistently under predicting the price, while very frequently under predicting the price. So this gives us an idea that this is not a very accurate model, and it is consistently under predicting. And by mapping residuals, we actually see that we are missing a variable, which is distance to water bodies. Well, I have a feature class for water bodies. How can I incorporate this into my analysis? Well, as a next step, I can add this particular feature class as a distance feature. And this tool will automatically calculate distances of every home to the nearest water body and use it as a predictor variable, as a second predictor. And when I look at the regression diagnostics for this new model, you might think that, well, we added a variable that our model really needed, so at least our R-square should go up. But when we look at our R-squared, it actually is pretty much the same as before. And the reason for that is, even though water bodies is impactful for the house price, the relationship is not linear. If you're 1 meter away from the water versus 2 meters away, your price doesn't just magically double. So this nonlinearity with respect to water bodies and house price cannot be captured by a linear model. And when we look at all of our diagnostics, this is the same conclusion we're going to arrive at. But we started simple. We tried to fit a global line to this whole data with one variable and two variables. That didn't work. Let's make it more sophisticated. Remember that Conquer BP statistic told us that there are some non-stationarity, some locally varying relationships. GWR can be a great candidate for that. But GWR, as Flora mentioned, is just a local version of GLR. We are still fitting a line. So how can we make sure GLR is going to work? Well, we can use a tool called local bivariate relationships. That is an exploratory tool that gives us an idea about what are the spatial relationships between these two variables I'm interested in at a neighborhood of 50. If I'm seeing colors that are not gray, so these different colors, this indicates that there are significant relationships and they can be linear, concave, or convex. If I would like to fit a local linear model, I would like to see a lot of dark pinks, positive linear, and a lot of dark greens, negative linear. Because if there is a local linear relationship, then I can capture this and model this with GWR. And another beauty of this tool are the pop-ups. After I run this tool, I can click on a location. In this location, at a neighborhood of 50, there is a significant relationship and it is linear. So this gives me hope that if I ran GWR, I actually can capture these relationships. Remember that grade was another important variable. It was linearly related to the house price, but globally, it was linearly related to the square footage of living. So we could not use them in the same regression model. What about locally? Are they locally linearly related? One thing I can do is I can do the same analysis between grade and square footage of living just to check if these two exploratory variables are linearly related locally. And when I go through that exercise, I unfortunately see a lot of linear relationships between these two exploratory variables, meaning that if I use them as predictors in GWR, I'm probably going to run into multicollinearity issues. And if you do not believe me, I did actually a run of GWR with these two variables with square footage of living and grade. And sure enough, the tool failed due to multicollinearity. So this was actually a very valuable diagnostic for me to do before going into GWR. So here we can perform GWR on square footage of living and price. Remember, this is going to be a local model. And this is the residual for GWR. One thing you will see is we actually have fewer darker colors, meaning that we have fewer over and underestimations. And let's quickly check the regression diagnostics for GWR. Now we have an R square of 0.89. So this went up from 0.49 to 0.89. And this shows you the power of incorporating space in a spatial problem. Just using a similar formulation, the same linear model, when it's solved with local weighting through GWR, a model that is 0.4 that has 0.49 R square can actually go all the way up to 0.89. And this is very powerful. And this gives us an idea that the goodness of fit of this model is almost twice as better than the global model. And another benefit of using GWR is seeing rasters. For example, GWR returns this raster that shows us the coefficient changes locally for square footage of living. So here in red, you'll see areas where small changes in square footage of living correspond to big price changes. And these are areas around water bodies. You should not pay too much attention to the eastern portion because we have very sparse data. But when we focus around the central King County, Washington, you'll see that the closer to water you are, the more impact you have, the more impact square footage of living has on the price. Meaning that if two houses are right on the water, and if one is slightly bigger than the other, its price is going to be much higher than the other one compared to houses that are more inland. GWR proved to be a very useful model, but one caveat to these linear models is multicollinearity. I cannot include all of the variables that I have. And that's one of the great things about random forest. It does not suffer from multicollinearity, and I can add all my variables and start exploring them in the context of my regression. And our random forest implementation is called forest-based classification and regression. Here I would like to predict price, and also I would like to predict, some of my predictors are categorical variables. And again, I can add water bodies as a distance feature, where the tool will automatically take into account that I'm calculating distance features. With random forest, you can also assess the uncertainty of your predictions, which is quite useful. When we look at the price and also the prediction interval, random forest will tell us that for higher prices, our model is going to have more uncertainty. You see that the bounds are increasing as price increases. The reason for that is we have less multi-million-dollar homes to extract patterns from. That's why, since we have more sparse samples at that price range, our model gets more and more uncertain. Another very useful output of random forest is distribution of variable importance. Here it tells us that the condition of the house and square footage of living are two most important variables. Distance to water bodies is the third most important variable that determine price. So this really gives us an idea about the drivers behind the housing market for King County, Washington. So far, we just trained the model. This model learned patterns behind what we were trying to model, but we can also do predictions. In other words, if I have new development, such as these new houses, and I don't have prices for them yet, but I know their attributes because I built them, I can run this tool in prediction mode. And I can input my new housing development as a feature I would like to predict. I can do the same thing for GWR. And in the last portion, I would just like to show you a comparison of prices. When I compare the square footage per dollar that is predicted by random forest in GWR, I see that the GWR predictions are more balanced and are actually quite similar to random forest predictions. And when we look at a scatter plot, we see that the values are quite comparable, but with GWR, we actually predict slightly higher values. But overall, since this model takes into account our spatial neighbors, with GWR, we can actually create a more realistic local model. With that being said, I'm going to quickly move on to our classification demo, which predicts seagrass habitats on the United States coast. The problem here is my data, unlike the King County house prices, doesn't come as a continuous variable, but it is a category. And here, this category is 0 or a 1. The seagrass species is observed somewhere or it is not observed. Again, we can check our scatter plot matrix. Here, my target variable takes a 0 and a 1, and it has these different relationships with my predictors. So this is a typical classification problem. One way to address this problem is through GWR. But this time, we can run it on binary or logistic mode, the same way we can add all of our exploratory variables. What is different here is, since I do not know a representative neighborhood, how many neighbors I can use, I can do a search for the best model for different neighborhoods and pick that best model. And when I run my geographically weighted regression, this is the deviance map. This is actually very good because I don't have a lot of dark colors, meaning that all of my predictions have very low mismatch. I am predicting correctly for the most part. And similarly, I can do this for random forest, where I can predict a categorical variable, where I tag it as categorical. I can input all of my predictor variables. Again, I can explore my variable importance. This tells me the most important variables, distance to port being one of them. And in the end, I just create a feature class that compares the mismatch between the two models. And whenever you see a blue, that means that both models predicted the same category. Whenever you see a red, you see that GWR and random forest predicted different categories. And this mismatch is pretty localized to a couple of points along the US coast. So overall, those 2 points do have agreement, because a complex global pattern can also be captured if indeed there are some linear relationships with a simpler local model. And this is basically the story behind this classification demo. And similar to King County, Washington, if you have new locations where you would like to predict habitats, you can easily do that. The last demo I would like to show is for death counts in Tokyo. Here, I have a completely different variable. I have counts. This is not continuous. This is not a category. And here, we have some counts that I would like to understand the relationships with respect to different coefficients. I can use a GLR model, which will basically be Poisson regression that will relate underlying variables to this death counts. And the variables we have in this particular data set are observed number of deaths, proportion of professional workers, proportion of owned houses, proportion of elderly people, and unemployment rate. And here we would like to understand the relationships. Again, the only difference is the model type I use. And when we look at the relationships here, we see in our diagnostics that the global model is actually not a great model to use because it has low predictive statistics, and it has variant inflation factor, which means that some of these variables were linearly related to each other. And when we try geographically weighted regression on the same problem, again, we use this on the count mode. We see that we get a much better model. And with the Poisson model, we actually can compare how good is this local model to the global model. And in this case, we see that the global model can only capture half of the variability, but with a local model, with this Poisson regression, we actually can capture 90% of the variability in this data set. And again, with anything GWR, we can easily assess the impact of different variables on death counts, such as unemployment, house ownership, population over 65, and so forth. So this is a holistic view of the type of predictions that you can do in ArcGIS platform, whether they are continuous variables, categories, or counts. With that being said, I will pass the mic back to Omar.
Thanks, Aaron. Okay, so I want to introduce you guys to a problem that we have been working with a lot of customers on in retail and banking, which is using machine learning to predict best areas to open stores or to launch marketing campaigns, which is obviously a geospatial problem. So we're not solving a new problem. It's the very existing old problem of choosing good locations. But we think machine learning has a very good chance of producing better results in many cases, as we're going to explain today. So questions like, what are the white space areas that we should consider for new stores? How can we tap into this without cannibalizing existing stores? Which stores should we consider for closure? Where should we allocate more marketing spend, and so on? So if you think about it, there are a lot of factors that can influence that, right? I mean, the kind of demographics, for example, the people living in different locations, the population density, for example, income levels, age groups, socioeconomic patterns, all of these are factors related to people living in different places, and obviously that's an important factor. Another aspect is really what we call the retail landscape, right? The proximity to existing stores, the proximity to competitors, the proximity to complementary stores, and so on. And if you think about it, with all of these factors, it's very hard for humans to find the best equation, if you will, right? But machine learning can find that equation nicely. If you can train the machine with historical performance data, and you can think of performance as sales or other metrics, like what we're going to explain, like the number of customer visits, for example, if you can get the performance data along with the other factors like the demographics and tapestry and proximities, you might have a way to train a model to make these predictions, right? So that's in a nutshell what we want to explore today. We want to help retailers and banks, and obviously any other segment who are interested in the same problem, use their historical performance data like sales, along with demographics and tapestry, along with spatial features like proximity to existing stores or competitors, to make these predictions. Where should we open new stores? So let's see how this happens in action. So if you think about it, if this is a customer, for example, so having this choice is influenced by, again, two major kind of like variables, right? One is the landscape itself. So for any customer, actually, you can think that they are exposed to a lot of options on a daily basis, not just like the nearest store, for example, but the nearest end stores, right? You might want to pick one on your way to work. You might want to pick one which is closest to your home if you're not going to work. If you're dropping your kids, for example, to soccer training, you might consider another one. So understanding what are the nearest existing stores is an important factor. So we are modeling the nearest 6 stores in that case, and we are using drive time and distance in kilometers for that. But stores on their own are not just the only factor. You have competitors as well. So the blue dots here represent competition, and we're modeling the nearest 6 competitors as well. And if you want to model on a block level the nearest stores and the nearest competition, this would be the nearest 6 stores and nearest 6 competitors for this block, for example, right? So in that case, we want to understand, we want to build this training data set, and we're using ArcGIS for this. So this is going to help us understand the retail landscape, but another factor is understanding who are the customers, right? So Esri have almost 6,000 plus demographic variables that are spanning, and this is in the US, we have different demographic variables all over the world as well. It varies by region, but in the US, you can look at like 6,000 demographic variables, and we have almost 67 distinct customer clusters in what we call the Esri tapestry segmentation. And this is a unique socioeconomic and demographic diversity found across the United States. So we want to add this factor as well. So we're going to add tapestry segments to our data. So I'm using ArcGIS notebooks, which, as you know, Jupyter notebooks brought inside ArcGIS. I'm using the ArcGIS notebook server in that case. So as you can see on my portal, I have different notebooks. I have different models. So I can choose this notebook here. And what I'm doing is I'm using Python to train a model with an external machine learning framework. So I'm adding the tapestry segments, as you can see here, building my training data set for each block. I am adding these different tapestry segments, and I'm calculating the proximities that you have seen as well. So in form of travel time and kilometers, and I'm calculating how many visits are happening from each block group to the nearest 6 stores. And I'm calculating these visits using human movement data. This is a very important aspect. If you have telecom data or human movement data, you can use this to model how many customer visits are happening. So as you can see, there are 2 visits into the nearest store. There are 4 visits into the second nearest store, and so forth. And this is going to be my label that I'm going to be trying to predict. And I'm going to train a model. I mean, this is a lot of data engineering and data processing I'm doing to prepare my data. And then I'm using gradient boosting, extreme gradient boosting, which is a very interesting machine learning model to use when it comes to performance and speed. And I'm splitting my data into training and testing data, training my model, and then I am deploying this model to use, right? So the way I'm going to use this model is this. I'm going to iterate all over the block groups and make an assumption that we're going to open a store at some location and run the model. So let's do this. First, I want to build a training data set for all of the block groups. So for each block group, I'm going to calculate the proximities to the nearest 6 stores and the nearest 6 competitors. So that's what I'm doing here. And then I'm going to build a forecasting hex bins. And in each hex bin, I'm going to assume that I'm going to open a store at a specific location, which is here, for example. If you think about it, if I add a new store hypothetically, I'm changing the retail landscape. So I need to recalculate the proximities to the nearest 6 stores, which is what I'm doing here. And then I'm making a prediction of the number of customer visits for this specific store if I open it here, and looping across all the block groups, I end up with something like that, a tessellation map showing the high potential areas explained by the most reddish areas, as you can see here. And it takes into consideration the existing stores and competitors. So you can see that there is a lot of potential at this area. And here, for example, although there are a lot of competitors, and this is something actually that was very useful to find out. Now we can do this for a whole state or a whole city, and we can do it across the whole country with the power of machine learning and geospatial. Another aspect that machine learning is really good at is finding influential factors. So gradient boosting or other tree-based algorithms can help you find that. So we can see here that the #1 factor is the proximity expressed by travel time to the nearest store. And then the third factor is a specific tapestry segment, segment 1D. So using Esri tapestry segmentation, you can go and understand more about this tapestry segment and see that they are interested in something specific, and understand who are the most important customers that you really need to think about when opening these stores. So using machine learning in that case has multiple sides. One side is helping you make the predictions. Other side is helping you understand why these predictions happen. So that was a quick overview of a use case that you can use machine learning for. You have seen how to integrate with external machine learning frameworks using ArcGIS notebooks and ArcPy and Python API. And with that said, I want to show you a couple of resources that could be really interesting. So real quick, the Spatial Analysis and Data Science landing page is a single page that can help you understand a lot of aspects about the different pillars of spatial data science, right? You can go here and click on any of these pillars, whether it's spatial analysis, visualization, big data, and understand more about each of these capabilities. If you click on events, you can see a lot of these webinars we've been doing. And these are on-demand webinars. You can go and register and watch the webinars, right? And there are some upcoming webinars like the video analytics with location intelligence as well. Another interesting resource is the spatial statistics page, where you can see a lot of tutorials, videos, presentations about supervised learning, unsupervised learning, clustering in ArcGIS. This is the page of ArcGIS notebooks, where you can use it to do a lot of these workflows. You can find it in ArcGIS Pro 2.5 plus and in server as well. It's coming very soon in online. These are sample notebooks that you can see to explore different use cases. This is the GeoAI Medium group, GeoAI blog post in Medium, where you can see a lot of these blogs. And finally, we have a group on LinkedIn, which you can see here, that we are building as a community for spatial data science and GeoAI. I really invite you to join. It's called the GeoAI group, and this is the link. We're going to share these resources with you by email, by the way, so don't worry. And with that said, I want to thank you so much for attending today. And I think we have a couple of minutes for questions. So Mallory, if you want to pick some questions, and you can answer them right now.
Hi, Omar. Yeah, we do have a minute or so left. So actually, why don't we take the very first question that came in? And Oren, I don't know if you mind answering this question. So question 1 was, if I wanted to predict the recovery of vegetation cover from scatter plots over an impacted tropical forest ecosystem within the next few years, what factors or tools should I consider?
That's a very interesting problem. So if there's a strong time component, I highly recommend waiting for 2.6 because we're going to have a new time series forecast tool, and that is going to be an auto regression, meaning that using the previous patterns of recovery, you can predict future recoveries. But if you think that there are covariates that are very important for modeling this problem, such as distance to nearby living places or any other ecological factor that you think is important or climatic factors, then you can use these regression models as well.
Right, thank you for that answer. The second question that came in, what is the loss type used for OLS under the hood? Is it squared error?
Yes.
Okay. Next question. Do we have flexibility to use nonlinear fit in GWR, like fitting GBDT for fitting the GWR? Sorry.
There is a forest-based implementation. I believe the GDBT refers to gradient boosting. So those methods are not as rigorous because GWR model is defined for linear models. So everything you've seen today, Poisson, binary, or continuous, is actually a linear solver. So GWR is not fully defined for nonlinear functions, but there is a random forest implementation of it, but it's not as rigorous. It's more of an algorithmic implementation. And the problem there is you can't really trust your diagnostics because you're not solving a linear system anymore.
Got it. Maybe we'll just take one more question. In random forest, is the sequence of questions asked set, or maybe that's in a set, i.e. the first dog question was big versus small. Is that set in the model? Is the sequence related to variable importance?
So I can take that one. The branches are split using something called Gini. So it's basically you're measuring purity. So you're looking at which variables would splitting them give you the most homogeneous groups. So let's say that I'm splitting, I just want to predict whether something is a dachshund or not dachshund. Let's make it binary to make it a little bit more simple. Which variable can I split in such a way that within the split groups, we have the dog breed that we're interested in more kind of like homogeneous in those categories. That's probably not the clearest way of explaining that. But basically, we calculate which variables make the biggest difference, which split is going to chunk up the data in such a way that the next split is going to lead eventually to the prediction. I don't know if Oren, if you have a more eloquent way on the top of your head of explaining
I think that's
information
great.
gain.
I think that's a great explanation. The only thing I would say is the split order will change because with random forest, as Flora mentioned, we are randomly sampling data. Just because we might have randomly sampled some subset where one variable didn't show as much variance, it probably is not going to be the one that we base splits on.
Mm-hmm.
Got it. All right, great. Since we are already over, I think that'll be the last question that we take, but I do want to close in saying thank you everyone for joining and sticking with us to the close of this webinar. Thank you, and we hope you enjoyed it and have a great rest of your day.
Thanks, guys. Have a good day.
Bye.
Bye.